Alright, hello and welcome to a video on physical quantities. So I hope that by the end of this video you're clear about these three questions and you're also able to gain a better understanding for this concept, which I think is one of the very fundamental concepts in physics. And I do apologize for my terrible handwriting, but I hope that it's good enough to pass. Um, and yeah, I think on that note, let's begin. So what are physical quantities? Let's start with that. So physical quantities are basically anything that you can measure, that you can physically measure. For example, speed or time or distance, displacement, etc. And they all have units. So, for example, length would be meters or centimeters, or you can have thermodynamic temperature that would be in Kelvin or degrees Celsius, etc. So there are these physical things that you can measure, and these things have unique units. So one important difference in physics is that when we write a unit, let's say meters or newtons, it's always written in upright letters. Whereas, for example, density, the quantity, is represented with the Greek letter rho. That's a terrible rho, but or you have mass, which can be represented with m. Now, the thing is that the quantities, they're always italicized to separate them from the units. Else one might get confused between this m and this one. So, just one thing to note and remember in case you ever get confused. Now, let's talk a bit about some of these quantities. Now, there are these 7 quantities called fundamental quantities. They are length, mass, time, electric current, temperature, thermodynamic temperature, amount of substance, and luminous intensity. And along with these different quantities, they have standardized units and symbols. Now, the thing is that these fundamental quantities all have very interesting definitions. For example, the second, it's defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium 133 atom. Now, I have no clue what that means, but it's interesting. And who decides these units and why are they considered fundamental? We'll come to all of that soon. But basically, these are the fundamental quantities from which you can find out any other quantity. Let's take speed as an example. So, speed, we know, is change in distance upon change in time, which can be measured in meters upon second, which can be written as meters per second or meters into second raised to power minus 1. So this sort of exponential form is what we consider as the standard in physics rather than involving numerators and denominators. So we can do the same thing for more complex quantities such as force. So force, we know, is given by mass into acceleration, which can be written in terms of the fundamental unit for mass is kilograms, so kg, into, now acceleration is change in velocity upon change in time, and change in velocity is measured in same unit as speed, meter per second, upon change in time in second. So it becomes kilograms meters per second squared, like that. So these quantities that we've derived are appropriately named derived quantities. Now it's important to note there are some units called supplementary units, which would include the radian, and the steradian. You must have heard of at least the radian in trigonometry, I presume. So we'll discuss these later, maybe in a future video where we're using the trigonometry especially. But for now, just know that they also exist, I guess. So let me take a slightly tricky derived quantity. Potential difference or voltage, represented by capital V, is measured in volts, right? So, but what is the unit for voltage or potential difference in terms of fundamental quantities? Just the way for force, we found kilogram meter per second squared, which is the same as newtons. So newtons expressed in fundamental units becomes kilogram meter per second square. So now if we have to do that for volts, we know that voltage is equal to work done per unit charge. Now work done is force into the displacement in the direction of the force. So the unit for force in fundamental units is that, into displacement would be in meters, right? Upon now charge, or Q. Q is given by the equation I into T, which in which I is current, electric current, and T is time. So we can write this as, in terms of the fundamental units for electric current and time, amp seconds. So we divide this whole thing by amp seconds, and we get kilogram meter square second raised to power minus 3 amperes. That is the fundamental unit for potential difference. Yeah, it is quite complicated, but hopefully you'll understand how to derive it. You don't need to remember it. Now you might ask, what is the point of needlessly complicating all of these units like newtons and volts in fundamental units? And the reason is because it helps in dimensional analysis. What I mean by that is that it allows you to do a few things, including verifying your formulae. For example, let's say you have just found out that the formula for speed, according to you, is distance upon time. So you can plug in the units of distance of speed on the left hand side, meter per second, and of the two quantities on the right hand side, meters and seconds, and you can see that since they both are equal, it's likely that your equation is correct. At least in terms of the unit, it's correct. Not sure about the constants, etc. So through this, we can say this rule that in an equation like this, the two sides have to have the same unit, is called the rule of homogeneity. So not only can we verify that our equations are correct, we can also do things like convert between different units. Let's say that one crazy physicist has given you the fact that they've measured some force to be 100 gram centimeter cubed meter second whole to the power minus 2. So you are very confused because this unit over here, neither have you nor has probably anyone else in the world ever seen. But what you do know is that force is measured in newtons, and you know that newtons can be expressed like any other unit in fundamental units. So what you do is you try and convert the non-fundamental parts, grams and centimeter cube, into fundamental units. So first you write it out and you multiply by 1 kilogram upon 1000 grams. Now this over here is naturally going to be the same as multiplying by 1, which doesn't change the equation in any way, but it allows you to cancel this grams with this grams as they're being divided, leaving you with 0.1 kilogram centimeter cube meter second raised to power minus 2. Now you could directly convert 100 grams into 0.1 kilogram, But as we'll see with centimeter cube now, at least whenever I try to do it directly, I often make a mistake. So we can now multiply by 1 meter cube upon, there are 100 into 100 into 100 centimeter cubes in a meter cube. So that becomes, so now from here, if I distribute the -2 over meter and second, we get meter cube into meter raised to power -2 into second raised to power -2. Now meter cube into meter raised to power -2 is simply meter raised to power 1. So essentially we get 0.00000001 kilogram meter per second squared, which, as you will remember, is the same as newtons. Now, under dimensional analysis also comes questions like this. Let's say you've been given that b, some quantity, is equal to sine a into t, and you've been given that t is distance measured in meters. Now you've been asked what is the unit of a and what is the unit of b. So the important thing to know here is that for all trigonometric functions and exponential or log functions, the argument of the function, that is to say this part, is dimensionless. Dimensionless basically means it has no unit. The reason why is quite interesting. I'll put a link to a great answer on why in the description in case you want to read more. But basically, if this a into t is dimensionless and t is measured in meters, that must mean that a has to be measured in 1 by meter or meter to the power -1, because when these two multiply, then the meter and meter will cancel out, leaving a unitless quantity. Now, as for b, to find out what b is, we can look at the nature of a sine function. So sine, what is it? Sine of any value theta, as we know, is opposite upon hypotenuse in a right angle triangle with the angle theta. So opposite upon hypotenuse, both of these are lengths measured in, let's say, meters. So once again, the units cancel out, meaning that this side or the result of the function is also going to be dimensionless. So in this case, b is also going to be dimensionless. So we can write a is in meter to the power -1 and b is dimensionless. Now, as I said, who exactly defines what are the fundamental units and what are the fundamental quantities? That is the SI, or this, which I have not learned enough French to pronounce. But this body of experts and scientists decide these rules so that there's a convention everyone can follow. And another thing they decide is some common prefixes. So now if we see the value we got earlier for force, it was really cumbersome to write it out. It had 1, 2, 3, 4, 5, 6, 7 zeros in it. So if I want to write that here, we have a way that you must know of to shorten this is we can use exponents and powers of 10. So we can write this as 1 into 10 raised to the power of -7 newtons. This way of writing is known as standard form. And in standard form, the general way of writing it is a into 10 raised to power b, wherein a must lie between 0 and 10, right? Because if it's less than 0, then you would decrease the exponent by 1, and if it's greater than 10, then you would increase the exponent by 1 instead of just keeping a as something greater than 10. And b belongs to the set of integers, and a belongs to the set of real numbers. So, but let's say instead of writing this in standard form, I want to write this in terms of one of these units. So these units, rather prefixes, basically allow us to represent the same information but with a more appropriate unit to the scale. Like if I have 10 raised to power minus 7, I can write that as 1 into 10 raised to power minus 6 into 10 raised to power minus 1 newtons, which can be written as 1 into 10 raised to power minus 1 micro newtons. Because you see that micro is 10 raised to power minus 6 and this is its symbol. Now this table is kind of confusing because it's made by Cambridge, worst publisher ever. Anyways, but if you just split it over here, I think it'll be very clear. On this side we have the negative exponents, this side we have the positive. So the smallest prefix we have is atto, then we have femto, pico, nano, micro, milli, centi, deci, deca, hecto, kilo, mega, giga, tera, peta, etc. As we climb up the ladder. So calculations involving the prefixes and standard form, uh, I suggest that you do some questions on it, because at least it took me quite a while to get a grip of it. And it involves majorly the laws of exponents, like when you multiply two values that are in standard form, as well as just being able to convert from one unit, let's say from micronewtons to something like kilonewtons. And yeah, I think that's pretty much it for this video. In case you have any queries at all, please feel free to reach out to me in the comment section or on, I think it's called the discussion page of the channel, and I'll make sure that I reply, or at least I'll try my best. And yeah, if you were paying attention in this video, then you should now be able to understand this. Yes, I do apologize for them being terrible, but I hope you enjoyed. Thank you so much for watching. Bye bye.